Our whole point is to talk about the theory and not to come out of this particular application, but to write on a whiteboard. And we're going to start, you guys, hopefully you guys already understand where the final position minus the initial position equaling to the initial velocity times cosine of the launch angle times t minus, well, plus 1/2 the acceleration, and that's a vector, this is a vector, times t squared comes from, as well as, and I'm going to call this equation number 1. Go ahead and make that clear. All right. And now I'm going to define equation number 2. We have our final position minus our initial position in y, and this is that y naught, x naught, you see x naught in the orange, and this is equal to the initial velocity, which is v naught, times sine of the angle, the launch angle, times the time of flight, plus 1/2. And you know what? I'm not going to use that plus. I'm going to go ahead and go with minus. My hope is that I've already defined 1/2 gt squared. This is equation number 2. So we're going to analyze these two equations. This is coming from our kinematic theory. We're going to analyze these two equations so as to find the initial velocity here, to find this initial velocity. So we want to know the initial velocity of the ball being launched out of the mini launcher. So let's go ahead and do that. So when the ball is launched out of the mini launcher, okay, we're looking for this. The acceleration is just going to be negligible. So there is some air resistance that's coming back like so. There's some air resistance, but the air resistance is so small that it has such the impact is negligible. So let's go ahead and say, since the force that's coming from the air resistance is approximately 0, we can let the acceleration in the x direction equal to 0. Thus, we can write the displacement in the x direction, because we have our final position and our initial position, equals to the initial velocity times cosine of the angle times the time of flight. The whole idea is that it's a simpler equation. So what just happened there? This is what just happened. This portion of the equation just went to 0. Of equation number 1, it just went to 0. All right. So you can have complicated equations, but you want to reduce them as much as you possibly can. And the experiment can guide you in that. So from this, let's just continue right on so we can know where we're going. The launch angle happens to be 0 degrees. Since the launch angle is 0 degrees, this implies, doesn't really imply, I shouldn't say imply, I'm going to say, therefore, we know that cosine of 0 degrees is just 1. So this cosine becomes 1. So now we end up with xf minus x initial equals to the initial velocity times time. So remember, we're trying to calculate the initial velocity here. So what do we need to do? Let's solve for initial velocity utilizing this equation. What do? We just divide both sides by t, and we end up with our initial velocity equals to the displacement in the x direction divided by the time that it takes for this displacement to take place. right. Trying to make those arrows right. Okay, there we go. So we need to be able to measure our displacement, and we need to be able to calculate our time. All right. We could calculate our time using the video, but I've shortened the video, so it's not going to really give you the proper time.